The Large Hadron Collider. It is near Genova in Switzerland, in Central Europe, which is Southern Europe. It's operated by CERN, and it is built in the 80s built Large Electron Positron Collider 100 meters underneath the ground. And it is 27 kilometers long. It is not a circle, it is an octagon, so of 8 sides. And it is the largest machine in the world, and it is cooled down to almost absolute zero, to 1.9 Kelvin. Now, and what happens there? There are strong magnets, strong electromagnetic fields who are kicking protons, one in that direction, the other one in that direction. They're kicking them always, if they pass it with one thing, they're kicking it on to the next part. One proton in that direction, other protons into that direction. And at 4 of these things, there are now other magnets, and they are trying to push them very small together. Protons are very, very, very small, on a very small places, so that actually, when at one curvature, hit exactly the other ones. And then they bang together. Now, and that works, and that the electric resistance of the magnets is not a break on them. They are super cooled down with helium, and also they are superconductors, these magnets. Now, and when they bang them together, then there are things to measure them. There's ATLAS and LHCb and CMS and ALICE. These are detectors. When they bang together, these protons, they are breaking up into gluons and quarks. And because we smash together, and inside of the protons, there are gluons and quarks. And when they are then detected, so first it goes on, there comes then concentric cylinders up in there. The first one is a semiconductor. So in that semiconductor, there the electrons very loosely bound. Semiconductor, you add just one electron, and it can conduct electricity. You take it away, and it does not conduct anymore. Now they come against it, and they are pushing basically at these loosely bound electrons when this semiconductor all them around, and you can see pretty much exactly where they were with gluons and quarks. And the next thing are the magnets, and they're pulling at them, and at the curvature it becomes clear how much they were pulled in, what the momentum of it was. Now, and then it is able to take that momentum at the next cylinder. So there's then at the next cylinder, there's now liquid argon and lead tungstate. And there these are stopped. Gluons and quarks are stopped in that very solid material. And when they are decreasing in speed, these gluons and quarks, they were accelerated, these protons, to 99.9999% of light speed, of speed of light. Now, when we're decelerating these quarks and gluons, then they're emitting photons. And these photons, the momentum can be now seen and calculated back to what mass they had. And the muons, they are going through it. These detectors out of lead tungstate and liquid argon, they are detected later. And the neutrinos, they are not detected at all. But it is able to calculate back what mass they had, because from the photons, how much mass the neutrinos had. No, neutrinos not. The neutrinos, they can be, if all is calculated together, what was measured, the subtraction of the neutrinos. Now the Higgs is the thing where it is calculated back. It is not, the Higgs is decaying too fast. But it is sometimes predicted to be decaying into high energy, a high energy pair of electrons, of photons, a high energy pair of photons. And it can be calculated how much Higgs would be there. Now, and if it's sometimes decaying into these high energy pair of photons, they can again measure it with a momentum and how much energy they had, with the magnets pulling at them, changing the momentum. It can be calculated back, translated back, how much energy that Higgs had, and how much mass it had. And now the Higgs has 125 gigaelectrons. And where the Higgs was discovered with the Large Hadron Collider on the 4th July 2012. And that is the Large Hadron Collider, and that is all according to the Richard Webb's particle physics book on the page 57 and 58. If you click this video away, then please tell me what the reason for it was, so that I can improve. Otherwise, hi and welcome. I'm trying to learn machine learning, mechanical engineering, and after we've done with it, we're going to do mechanical engineering, the Large Hadron Collider. And after we've done it, we're going to do Neckstretching. And if you participate in the Neckstretching, then it's better at your own risk. Now, we had so far the Large Hadron Collider. It is 27 kilometers long. It is the biggest machine ever built. It is running at almost absolute zero, at minus 270 degrees, at 1.9 Kelvin. And there's something else. It is built on the site where once the Large Electron-Positron Collider was 100 meters below the ground. Use something else. And there are many different compounds needed to build that whole thing. And they switched it on in 2008. I think that other things. There was something else. Okay, the next thing. It is not circular, it is an octagon. So it has 8 sides, but it's almost like that. It is called the LHC, the Large Hadron Collider. It is operated by CERN, which means something also. And in that, protons, for example, I think we can also do other things, but protons, they are accelerated faster and faster every time by very strong magnets, made very faster, and other magnets making protons into the other direction. Then we put it closer and closer together until they suddenly collide. They are accelerated to over 99.99% of light speed, of the speed of light. And the magnets are supercooled and also superconducting. Now, on four of the octagon sides, more magnets constrain the proton beams to a fraction of the thickness of a human hair. So on 4 sides, there are other magnets, and they are putting these protons very, very small together, a fraction of a human hair, and bring them onto collision course with the other protons going into the other direction. 4 large detectors record the result, one at each point: ATLAS, CMS, LHCb, and ALICE. ATLAS and CMS are all-purpose detectors, designed to measure whatever pops up, including the fleeting trace of Higgs bosons. So ATLAS and CMS, they are recording just everything. They are trying to find traces of the Higgs boson. When 2 protons collide at the heart of the LHCs, of the Large Hadron Colliders, ATLAS and CMS detectors, they split into their constituent quarks and gluons, which decay further into myriad particles spraying out in all directions. It is the detector's job to measure or identify these collision products. So when we are putting these products together, they are breaking apart. And now it comes out what is inside of them. So there's not just the atom with the electrons, and inside of the atom they have the protons and neutrons, but inside of the protons are things. And there are the quarks and gluons. And if you smash them together, these protons break, and the quarks and gluons come out, or their further decay products. And that should be detected by ATLAS and CMS. They are then further decaying into myriad particles. I haven't paid proper attention, I don't know what myriad particles are. Each detector is made up of concentric cylinders. So cylinders? Those closest to the collision point are made of a semiconductor. Okay, we're having a semiconductor. If an electrically charged particle passes through a semiconductor, it liberates the material's loosely bound atomic electrons, creating a pattern of electrical currents that allow precise measurement of a particle's path. Magnets surrounding the detector cause the paths of the charged particles to curve, with a degree of curvature representing the particle's momentum. What is the momentum? I thought they had the movement it has on it through the electrons. I understand that bit. They have cylinders, and there are a lot of electrons, semiconductor electrons. Semiconductor work like that. There's just one electron, I don't know if it's not an electron or not, but if a semiconductor work like that, they are able to, you put just one electron in it, and they're becoming positive, and just one electron away, and they're negative, or something like that. So semiconductor, they are half conducting and half non-conducting. You can make them very easily with just adding one little electron, one little atom, conducting materials, and one taking away not. Such a book is almost not conducting. Iron is very good conducting, and the semiconductor is the middle. You put a little electron to it, a little thing, and now it is conducting good, and you take a little bit away, and now it's not conducting anymore. That way in computer, you can say how it should work. You make a hard drive with billions or whatever of these semiconductors, and if you put an electron in, that sort of electricity just running, you put an electron in, and now the thing is charged, and now it represents the number 1. If you put that 1 electron away, and it is no longer conducting, I don't know how it works exactly, it is no longer conducting, then it is a 0. And that way you can write with just 1 little electron, so it's just a part of an atom, so very, very small, millions of things, just 1 electron per number. And you can make with a little bit of energy out of the charging, out of a battery, billions of switches, billions of times you can put an electron in and out. Electrons are just current. So you can put a little bit of electricity, just 1 electron in, and you have written down a 1. You put the electron out, and you have a 0. In that way you do it millions of times per second, and you can make millions of 1s and 0s, and 4 1s mean the letter H, and 4 1s mean the letter I, whatever. And that way you can then write words and numbers, and that way the computer is calculating. It's just putting billions of millions of these electrons in things and taking it out, in and out, in and out, and every time that makes a switch on and off, it says it's charged or uncharged, charged or uncharged. We have a semiconductor. You put 1 electron in, it is charged, it is conducting, you put it out, it is not charged, it is a 0, and so on and on. You couldn't do it with just 1 battery, billions of these things. That is how computers work. Now, my idea is that there are this semiconductor in a cylinder, the particles come into it, act onto these electrons, switch their charge, and now you know exactly where the 1s and 0s are technically or something, and you know exactly where the electrons have come to and not, and you can basically, like a scar, you can see where it is. I have no idea if it looks like that. I already have it here. Magnets surrounding the detector called, that's the other thing. If an electrically charged particle passes through a semiconductor, it liberates the material's loosely bound atomic electrons, creating a pattern of electrical currents that allows a precise measurement of the particle's path. So it's liberating when the little electrons there, because the other thing has also some type of energy, and then you can see exactly it was here, it was here, it was here, it was here. It was there. And the other magnets surrounding the detector cause the paths of the charged particles to curve with a degree of curvature representing the particle's momentum. I don't understand that part. The momentum is where it goes. Whatever, there are other magnets, and we're curving it, and through that we get the momentum of a particle. The next cylinder outwards consists of detectors filled with liquid argon, or lead tungstate crystals. So when there's liquid argon, or tungstate crystals in the next cylinder. In Atlas it's argon and CMS tungstate. Collisions with the densely packed atoms in these detectors stop most particles in the track, and photons emitted as the particles decelerate can be used to measure the particles' energy and so identify them. Okay, there's argon, liquid argon, and transducent tungstate crystals. Tungstate. At Tombstone, Arizona, there was a famous battle of Wild Earth, or famous shooting. It's tungstate crystals, like the other thing, tungstate. Tungstate. Okay, tungstate and argon, they're the things. Liquid argon. Now the atoms are stopped. And why? I think because they are stopped there. Photons emitted as the particles decelerate can be used to measure the particles' energy and so identify them. They stop there, and then they are emitting photons, and these photons they can measure how much energy they have. These photons can be captured. The heavier variants of electrons, known as muons, aren't stopped by these detectors. So the muons going through, but are identified and measured by the next cylinder of dedicated detectors. The even more reclusive neutrinos. They don't say how. There's another cylinder for the muons. The even more reclusive neutrinos aren't measured at all. Their presence is instead deduced by totting up the momentum of all the other particles produced in a collision and seeing if anything is left unaccounted for. The neutrinos are not detected, and also other things there, but they have detected all the other things, and the missing thing is the neutrino. The Higgs boson is short-lived, decaying almost instantaneously into other particles. To infer its presence, we must measure these decay products and look for evidence that they come from a Higgs. Fortunately, the standard model predicts everything we need to know about the Higgs boson apart from its precise mass. For every possible mass, we can predict the number of Higgs particles that the LHC should produce and what we will decay into. So it is able to predict from the mass of the protons which were collided how much Higgs particles there would be. For example, now we're not going to continue now. We need another part to go with it. What did we have? We had the basics data, and when we had it was accelerated to 99.99 speed, then banged against each other. By that the quarks, it breaks apart and the gluons and quarks come out. And when Atlas and CMS, we are detecting them. And now the first cylinder, they are each a concentric cylinder. I don't know what it means, but I think it's a concentric cylinder. I have maybe a little thing here. Yeah, it's somewhere in the picture. Okay, whatever. A concentric thing. Cylinder. So it goes through a semiconductor, liberates where the electrons and leaves a pattern. Other magnets are pulling at it, and the way it curves then represents the momentum of it. Next cylinder is liquid argon or tungstic crystal. They are where stop the most things, and the photons emitted by this deceleration process are then measured. And now it's known how much particle energy was there. And when the muons, they are flipping through, but they are detected by the next detector. How is not written here. The muons are not detected. No, the muons are flipping through. The neutrinos are not detected at all. But after totting up, as you use the word, after totting up, I don't even know what it means. After totting up all the other momentums of all the other particles, it is the rest which stays left. Higgs boson lives shortly, but it is possible to predict how many Higgs boson there are, depending on how much protons were collided. And we're going to read on the next slide. If you were here for mechanical engineering, you can go directly to the next part of mechanical engineering. If you stay here and participate in the Neckstretching facility, the legs are standing shoulder width apart, we're breathing in and reaching the fingers as far as possible. Meaning now reach as far as possible. Taking up. Reach as far as possible. And down. Reach in front. Up. Back. And down. And another time. Have feet standing together, arms to the side and circle around. Other direction. And legs again, shoulder wide apart, toe up, shoulders back, breathe in. And out, and calmly turn the head over to one shoulder. Breathe again in. And out, chin down to the clavicle. Breathe again in, lift your gaze. Turn the head over to the other side. Breathe again in. Out, chin down onto the clavicle. Breathe in, lift the gaze. Back into the middle, out. First side again. Breathe in. And breathe halfway out. And then circle the head over. Breathe again in. And halfway out. And then circle over. Back into it. The palms together. Breathe in and reach high. Now with the elbows also together. Palms and elbows. Breathe in and reach high. Down and down. In and up. Down and down. Elbows back. Breathe in. Out in front. Head down. Breathe out. In. And out. In. Feet together. Breathe in. Lift the arms up. And breathe out, lean back, drop a shoulder bits together. In and up. Out and back. In and up. Out with hands down. Breathe in the arms up. Out and down. In and up. Hands to touch and now towards it. That was a short next stretch. We don't have more time left. I thank you very much and until next time.